Hi there and welcome to this video for Senior Physics on Motion. In this video we're going to explore the concept of centre of mass, which is going to lead on quite nicely into our next video, which is going to look at momentum. Now, centre of mass is basically a useful tool for studying collisions, explosions and other forms of motion where we've got two objects coming together, where there's actually going to be an object. Where there may be a crash or what have you, and we look at them as like one full closed system. So we tend to use what's happening to that center of mass as a baseline, and from this we can then calculate a variety of different things, especially when we're looking at 2 and 3 dimensional problem solving. Now, center of mass is basically the point where the total mass acts. Now, on the planet Earth, our center of mass basically will act downwards affected by the force of gravity. So as a result, it's often called the center of gravity. Now, you've heard before probably center of gravity being used a lot in things like any form of like rugby. If you're going to be tackling someone, a smaller guy can basically be harder to get down because for changing their center of mass it varies. Also, if you have a low center of gravity, you can get underneath a taller person, tackle them and put them to the ground. So the idea is that center of gravity has an effect with respect to how well you can place yourself, and by placing yourself in specific positions, you can be very, very strong on your feet, and the result is you can be very static. Now, this becomes very, very important when we look at architecture and the engineering that goes into the design of the bases of buildings. Now, why do you ask this? Well, if you think of any type of building, the result is that a building will be subjected to the effects of the ground. So in an earthquake, for example, or if you're building a high-rise building, it will be subjected to wind. Now, all buildings have the ability, just like a tree, to move. Now, if you move a building and the result is the center of mass moves across the baseline area, then the result is you're likely to get your baseline, your building to crack, and it will fall over. Basically, the old adage that a building is only as good as the foundations is true in this case, because if your foundational support is too narrow, then the result is that the thing will topple over. Now, take the idea of a pyramid. Put a pyramid on its point, it will fall over. Why do the pyramids in Egypt stand erect now after being built over thousands and thousands of years? They've got a big base, and the result is the center of mass basically is right over the center of that base, so it's very, very static, very, very strong. So let's have a look at this in a more diagrammatic version. So here we've got two scenarios. They're made up of two buildings. Now, the two buildings basically are trapeziums, so as a result we've got all of the mass acting in the center. Now, I've noted that the center of mass, or COM, is acting straight down due to the effect of gravity. Now, in the first diagram, what we've got is the center of mass is acting inside the base of our building. As a result, the building is going to be stable. This means that if wind is actually attacking our skyscraper, for example, as long as the center of mass stays within the confines of the baseline, then the building should be static. However, in the second diagram, we see that the center of mass, the building has moved such that the center of mass is not being held up by the base. As a result, the building will eventually fall over. So a good example of this is the Leaning Tower of Pisa. Now, you can see the Leaning Tower of Pisa here. We all know it's a phenomenon where the building, basically due to subsidence, has actually moved and is sitting on an angle. Now, there was a time that you used to be able to go up the Tower of Pisa, but with time, what's happened is the constant use and weight of people going up the tower has caused the subsidence to actually increase to the point that it's now unsafe. Now, you can see here I've put a vertical line to show the center of mass acting straight down. Now, at the moment, you can see that it's on the base, but it's moving away from that vertical line, which is going to make it a danger. So as a result, due to the foundation subsiding, the tower is leaned, and then basically if the COM gets any closer to that edge, what will happen is the forces generated in the building itself, the weight forces, will cause it to collapse. So as people, as I say, have walked up, the COM has shifted over time, and eventually, if it's not supported, the result is the tower will eventually fall over. Now, as in engineering, it's really, really important now that we actually make a material that allows the weight or the forces which are generated due to any movement of the building to actually have some elasticity. That elasticity can, as a result, deal with the movement. We also need to have countermeasures to, if we've got a whippy type of building, that can counteract it. For example, putting weights on the top of the roof to counteract the movement of the building, or by having shock absorbers in the foundations so that the center of mass is always over the base. The closer we can get it to the center of the base, the more stable the building will be. Okay, so what I've done is put a video together to try and show some examples of center of mass and how we can calculate them and use them. So do watch that video, and hopefully it will explain what I've just illustrate what I've just explained here. Now, another way that we can deal with center of mass is by using mathematics. We can look at the mathematical components which basically have occurred. In a lot of cases we call these taking moments, and it uses the concept of the equation torque. Torque is basically a turning force. It's the force which is going to turn an object around a pivot point. Now, torque can be calculated using the force of the object and the distance that happens to be from the pivot point. So basically, torque is going to be T, measured in Newton meters. The force is going to be in newtons, and the distance is going to be in meters. Apologies there's a slight typo. Instead of nm to the -1, it should be n times m. So torque is Newton meters. So basically what we've got, if we take a scenario here, we've got a guy who's in a state of equilibrium. And what equilibrium means is that the forces on both sides of the pivot point happen to be the same. Now you will notice that the distances here are different, S1 and S2. Why is that? Well, the reason why he's still in equilibrium is that we're not interested really in the distances or the forces. We're looking at the combined effect. The torque on the left-hand side is basically being made up of a large force and a very small distance, or small s1. So F times s1 will equal a specific torque. Now on the other side of the pivot point, we've got less of a force, but the distance is increased. Now, because he's in equilibrium, the changes in force from the left-hand side to the right-hand side is a direct ratio to the changes in distance. So as a result, for S2 times F, it's going to be exactly the same turning force as the force times S1. So it means that both forces are acting in the same direction. So his hands basically will take all of that weight acting down, and as a result, he will be stable. So in this case here, what we'll notice is that we've got S1 and S2 are going to be equal. So T1 and T2, or the torques around that pivot point, will also be equal. So T1 and T2 therefore are in equilibrium, as S1 and S2 are also the same. We notice that obviously the forces will have to be the same. So as long as the torques are basically maintained either that around that pivot point, then the result is we're going to get no movement. So let's have a look at an example here where we can utilize the center of mass and work out what's happening either side of an object and state whether it's going to move in one direction or another. So here we've got some masses of 4 kilogram and 10 kilograms are on the ends of a 1.2 meter long bar as shown in the diagram. We're going to determine the center of mass of the system. So in this case, we notice that point C is located at a certain distance S from the 4 kilogram mass, and we know that 1.2 minus S meters from the 10 kilogram mass. So for the bar to balance, we need to make sure that F1 times S1 equals F2 times S2, noticing that the pivot point is at C. So if we say that F2 is on the right hand side of our diagram and F1 is on the left-hand side of the diagram, then as a result we can basically work out what's going on. So in this case, what we get is we're going to get 40 times S equals 100 times 1.2 minus S. So as a result, we get 40S equals 120. So S is going to be 0.86. Now, in this case, what we'll notice if we then calculate them accordingly, we're going to state that the center of mass in this system is going to be balanced because we've got the torque on one side equaling the torque on the other side. So the center of mass for this system is in the correct place, and as a result, the whole thing will balance. Again, watch the video that I put on, the practical video, which will explain and show you some neat things that you can work out with respect to center of mass and how it all works together. Okay, so as I say, check out the practical video, and I look forward to you joining me again. Thanks for watching.